Hello, this is an explainer video for my equations that I use to make this dart shooter actually function. So if we can just get into it. This is the situation where the dart shooter is above the target. So it kind of helps to describe the specific situation that the dart shooter is in. So there's a specific angle of the dart shooter, which I'm calling theta. There's an initial velocity that the dart is leaving. There's a delta x, or I use capital R as in range, that the dart's traveling, which is really what we're interested in. And then there's a height above the object that the dart shooter is, called y1. So to first make an equation, like a general equation, I really just tried to solve the problem, give numbers, give specific values for the situation and solve, and then kind of work backwards from there. So I just made up numbers. Y1 was 1 meter, initial velocity was 2 meters per second, and the angle of the shooter was 45 degrees. And I was trying to solve for the range, or R. So first, I have to solve for the time it takes for the dart to go from the bottom of its travel to the top. So from here to here, which I call T up. So using the kinematic equations, you can solve for T up, or I'll say TU as well. The final velocity y minus initial velocity y over acceleration, which was just negative 2 sine 45 degrees over the Earth's gravity, negative 9.8 meters per second squared. And then to find the change in y up, which was basically the height difference from here to here, delta y up from here to here. I just used, this is just for general delta y, and then initial velocity y times t plus 1/2 acceleration t squared. I just plugged in the numbers that I already solved for, specifically time, the 0.1443 number. So I got delta y up, as in the dart goes 0.102 meters from here to here, so it goes an extra 1.02 meters. And then to find the time down, so the time it takes the dart to go from here all the way down to the ground, or the object, target, I use that same equation, delta y equals VIT plus 1/2 acceleration t squared. So we know the initial velocity, y, at the top of the range is 0, because we're at the exact moment where all of the velocity in the y component is at 0, because it's perfectly leveled out. It's not approaching the level or going from the level. It's perfectly at that point. So the initial velocity y would be 0. So you're just left with the 1/2 acceleration t squared, and you can solve for t from there. 2 times delta y over a. And then you can actually solve for t, where we use the, what is it called? It is the the delta y up plus y1. So 2 times that, divide by 9.8, take square root. And then you get t down, so you can add t up plus t down to get the t total, time total. And then to find the actual range, what we're going to do is multiply the initial velocity times cosine theta, which gives you just the horizontal component of the horizontal component of the velocity multiplied by the total time it takes from the shooter to the dart from when it's shot to hit the ground. And then you get 0.856 meters for the range. And then now that I did it once, I can start working on a formula. Oops. So obviously T total just equals T up plus T down, TU plus TD. So I already had that equation for TD, root 2 delta y over 9.8. And then I also had the equation for TU, which is a lot simpler, just VIY, initial velocity in the y component over acceleration. And then I expanded it a little bit. The actual change in y delta y equals, it's the change in y up plus y1. So remember the delta y up was the change in y from the ground level that the dart's being shot to the highest point in the like parabolic arc that it takes. And then I work symbolically to create the formula. So VIY is to find the change in y up. I used this is one of the basic kinematic equations. I plugged in symbolically, so VIY, initial velocity y, is the initial velocity times sine theta, the angle of the dart shooter, times, so T, we found T to be just T up. This is just T up because the delta, this is at the top of the arc, and the only time that's passed is the time that's needed to go up, which was just the initial velocity y over acceleration, which was 9.8, minus 4.9. I just combine these two terms. A is always negative 9.8, and 1/2 of 9.8 is 4.9. And then t squared, I just put VI sine theta squared, or over 9.8 squared. And when you simplify it, you can pull out V initial velocity squared sine squared theta. And then, amazingly, I don't know how, but it simplifies to 1 over 9.8 minus, this is, what was it? It's 4.9 squared over 9.8 squared simplifies to 5/98. I don't know how, but it does. They're basically the same exact number. So then you can have a more generalized formula for delta y up. Oops. And now that you have delta y up, you can make an equation for t total, which this is just t up and t down. Was this was just simplifying or plugging in that 2 delta y over 9.8 square root. So there's that y1 right over there. So the actual range is the initial the x component of the initial velocity, so vi cosine theta times the total time, which was this large unit over here. And that was the equation for the range. So vi cosine theta bracket vi sine theta over 9.8 plus the square root of 2 parenthesis vi squared sine squared theta parenthesis 1 over 9.8 minus 5 over 98 in parenthesis plus y1 in parenthesis all over 9.8. That was the range that I found. And this is just for this specific example where the object is below the shooter. So I hope you enjoyed that. I hope my explanations were clear enough. It's kind of complicated if you don't have experience with it. Leave a comment, maybe if you don't know. So I hope you enjoyed it. See ya.